Hello students, welcome to the YouTube channel Physics Simplified. Here, we will understand numerous concepts of physics from a numerical perspective. So, without any further delay, let's jump into the discussion. Topic of discussion for this video, magnetic field due to a moving point charge. In this problem, a point charge of 5 microcoulomb is moving at a constant speed of 8 into 10 to the power 6 meters per second along the positive y direction with respect to a reference frame. We need to find the magnetic field at the given points when the point charge is located at the origin of the given reference frame. Before start solving the problem, first we will identify and set up the necessary equation required to solve this problem. To solve these types of problems, we need the expression of the vector magnetic field, that is, vector B, due to a moving point charge. Once we have this equation, we will then use it to find the magnetic field vector at each of the given points. Suppose we have a single positive point charge, Q, which is moving with a constant velocity, v. We call the location of the moving charge at a given instant as the source point and the point where we want to find the field as the field point. The magnitude of the magnetic field vector, vector B, is given by B is equal to mu 0 by 4 pi times qv sine theta divided by r squared. Here, mu0 is the permeability of free space, r is the distance of the given field point from the point charge q, and theta is the angle between the line from source point to field point and the velocity of the charge. The magnitude and direction of the magnetic field can be incorporated into a single equation by using the cross product. So, the magnetic field vector is given by vector B is equal to mu 0 by 4 pi times q vector v cross r hat divided by r squared. R hat is the unit vector that points from the source point to the field point. This unit vector is equal to the vector r from the source to the field point divided by its magnitude. So, the above equation becomes vector B is equal to mu 0 by 4 pi times q vector v cross vector r divided by r cube. The direction of the magnetic field is perpendicular to the plane containing the vector r and vector v. Now, we will use this equation to calculate vector B at each given point. According to the problem, Q is equal to plus 5 microcoulomb, which is equal to 5 into 10 to the power minus 6 coulomb. Since the point charge is moving towards the positive y direction, hence, vector V is equal to 8 into 10 to the power 6 meters per second j hat, because j hat is the unit vector along positive y direction. So, V, the magnitude of the velocity, equals 8 into 10 to the power 6 meters per second. For part A of the problem, the coordinates of the field point are x is equal to 0.5 meter, y and z are equal to 0. Therefore, vector r is equal to 0.5 meter, I hat, where I hat is the unit vector along positive x direction. Now the cross product of vector v and vector r is given by vector v cross vector r is equal to v j hat cross r I hat. Now j hat cross I hat is equal to minus k hat. So vector v cross vector r is equal to minus v r k hat. So, the magnetic field vector, vector B, becomes equal to minus mu 0 by 4 pi times q v r k hat divided by r cube, that is, vector B equals minus mu 0 by 4 pi times q v divided by r squared k hat. The value of mu 0 by 4 pi equals 10 to the power minus 7 Tesla meter per ampere. Substituting all these values and simplifying the calculation, we obtain vector B is equal to minus 1.6 into 10 to the power minus 5 Tesla K hat. This means the magnitude of the magnetic field is 1.6 into 10 to the power minus 5 Tesla, and it is directed in the negative z direction. For the part B of the problem, the coordinates of the field point are x and y are equal to 0 and z is equal to 0.5 meter. Therefore, vector r is equal to 0.5 meter k hat, where k hat is the unit vector along positive z direction. The cross product of vector v and vector r becomes vector v cross vector r is equal to v j hat cross r k hat. Now j hat cross k hat is equal to I hat. So vector v cross vector r is equal to v r I hat. So the magnetic field vector B becomes equal to mu 0 by 4 pi times q v r I hat divided by r cube, that is vector B equals mu 0 by 4 pi times q v divided by r squared I hat. Substituting the values of all the quantities and simplifying the calculation, we obtain vector B is equal to 1.6 into 10 to the power minus 5 Tesla I hat. This means the magnitude of the magnetic field is 1.6 into 10 to the power minus 5 Tesla, and it is directed in the positive x direction. So, we find that for each of the two given points, the magnitude of the magnetic field is the same, but the direction of the field is different for the 2 points.